Well, good evening everybody and welcome to the Planets and Moons chat live from here at the Open University in Milton Keynes. I'm Dave Rothery, I'm Professor of Planetary Geosciences here at the Open University, and I'm very pleased to have next to me my colleague Susanne Schwenzer.
Hello everyone.
Now we're here mostly to answer your questions and we'll get to those in a little while. But I just want to point out, if you look below us on the screen, you should see some widgets. There's a map. We'd love to know where you are. We'd love to know what you're studying or have studied. And you're voting already on where you think we should send humans next, the Moon or Mars. The rest of you might like to hold off that till near the end. You might hear something which makes you want to change your mind. Maybe you can change your vote, I don't know. Anyway, it's good to see these widgets in use. So before we go to your questions, we'll tell you a little bit about ourselves. Now, I know Susan as somebody who drives very carefully, very slowly around the surface of Mars. So, Susan, tell us about your adventures on Mars.
Yes. Yeah, I'm actually a mineralogist by training, and mineralogists, these are people who couldn't really decide whether they wanted to do chemistry or earth sciences, and so they went down the middle road. And for my PhD, I got into studying Mars already, starting with the Martian meteorites, but these days I'm actually working on the Mars Science Laboratory rover team. And here is a model of the rover. And what you see, first of all, that's made from Lego, but you see that it has wheels which are all in a very complex suspension system. And on the real rover, each one of them drives individually and has its own motor. But more important for us as a scientist is what instruments are actually on this rover. And there you have the mast with its cameras. And you might see this little red dot in the middle of this camera head, and that indicates the laser we have. We can shoot rocks at a distance from up to 7 meters and find out its chemistry. And then we've got more cameras on the rover. A couple of them are actually under the rover belly. These are the hazard cameras. And the hazard cameras, they look at the surface in front of them to detect that we are not accidentally driving into something that's too big to drive over. But back to the science, we've got this arm here, and this arm has a camera as well, where we can get really close up of the rock, like a hand lens, but also it has a chemistry instrument, the APXS instrument, where it can study the chemistry of rocks.
That's an X-ray spectrometer.
Yes,
yeah?
alpha particle proton X-ray spectrometer.
Right.
And the good thing about alpha particles is you couldn't use this instrument on Earth because you've got the atmosphere. And so if you've got the atmosphere, that would basically slow down your alpha particles too much to measure anything. But on Mars, with its very thin atmosphere, you can actually use alpha particles like you use X-rays here on Earth.
Okay.
And this also has a rock preparation tool, and that is where it becomes really interesting for 2 other instruments. We can scoop and drill rocks here with this arm instrument and put them into the rover belly, where there is the SAM instrument and the ChemIn instrument. The ChemIn instrument does mineralogy, like is this a pyroxene or an olivine, for example. And the SAM instrument does volatiles, CO2, noble gases, all these things. So that's a very brief tour around the rover.
And now this has been driving around inside Gale Crater for over 3 years now.
Yes,
yeah?
yes. We are actually in Sol 1277.
Sol is a Martian day, yeah?
Sol is a Martian day.
Longer than an Earth day.
It's just 30 minutes longer, roughly.
So what has Curiosity seen?
Curiosity has seen a lot of things. I mean, in 3 years, you see a lot of things. And part of that is to investigate the landscape. And what we found is actually a lake bed with all the things that come with it. And our first drill is a mudstone. And maybe we've prepared a video. Actually, no, we have prepared a video. We've brought a video that NASA has prepared, which shows a little bit where we've been at in the very first year. And here it comes.
So it's highlights of the first year.
Yes, it highlights, it's 500 something pictures from the first year from these hazard cameras that I just pointed out. And it drives over the surface, and then you see the arm gets deployed. And this is our first target that we brought into the rover, because you see this is a little sand dune, and it gets scooped a couple of times, and then the last scoop is actually sieved, and the fine material is put into our rover instruments. And what we found was really, really interesting, because we found all these unaltered minerals like olivine or pyroxene. Those of you who have studied anything about earth sciences or planetary science know that these are the minerals that don't weather very easily. And then we've driven on.
They do weather easily. You wouldn't find them on Earth. They'd weather away.
Yes.
On Mars they survive.
Did I say anything different? Sorry. No, on Earth they weather away very easily, and on Mars they survive, as you just said.
Yeah.
Thanks for spotting that. And you see here now that we are doing a lot of activities with the arm. If they are very short, it's just taking the APXS instrument down. But you will also see one time where we put the arm down for quite a while, and you see how the light changes. And that's when we drill a hole, which takes really, really long, probably 2 weeks our first hole. And then what we found there were all these clay minerals that show that there was water in the subsurface of Mars to alter these olivines to clays.
It looks like a mudstone. A geologist would look at that and say fine-grained sedimentary rock.
Yes, and the Mali image on the arm, the Mali lens on the arm, they showed really that it was smaller than usual silt grains, so it was a really, really fine grain, and we couldn't get any resolution out of it. And so here we are driving along, and this whitish-looking thing is Mount Sharp, or Aeolis Mons. Aeolis Mons is the official name. It's a little bit too light-toned in this image, and here you see NASA produced this, and it's something like 448 images from the first year of the mission.
And since then it's begun to climb higher and higher up Mount Sharp.
Yes, we are on the way to Mount Sharp. We are in the middle of the dune field. We have investigated the dunes, and we are on our way to Mount Sharp.
Brilliant.
Yes, but Dave, I've spoken about my research a lot. What about you? What do you do?
Okay, well, I'm working on Mercury. I'm involved in the European Space Agency's mission to Mercury, which is called Bepi Colombo, and we're going to launch in a year and a half's time, but we'll get to Mercury in late 2024. So that's a long wait, but in the meantime I'm working with data from NASA's Mercury mission called Messenger, and it's a wonderful planet. It's rich in volatile elements, which it shouldn't be that close to the Sun. If you want to find out about Mercury, we've put some resources online with the aid of the European Space Agency. We can show you the URL on screen. We are showing you the URL on screen now, I think. There's a transit of Mercury on the 9th of May. Mercury's going to go across the Sun. So we've got a load of resources where you can learn about Mercury, and a list of places where you can go and see the transit for yourself. Hook up with your local astronomical society or your local university. If you're in Milton Keynes, come and join us here. If it's cloudy, you can watch it on a web stream, because ESA have satellites in space which will be watching out for this transit, and will be web streaming those images, and from solar telescopes.
Yeah, but there's one thing you shouldn't do, and that's probably pointing your own telescope at it.
Yeah, if you don't know what you're doing, do not try to look at the Sun. If you point a telescope, binoculars, or even a naked eye, it's too small to see by naked eye anyway, but if you stare at the Sun, you're going to damage your eyes, and especially with a telescope, don't do it. If you want to try, you need to project an image onto a white card. If you've got a proper solar filter, not just a bit of darkened glass, a proper bespoke solar filter, and you know what you're doing, fine. Otherwise, don't try and look at the Sun. Go to the people that know what they're doing. Your local astronomical society will have solar telescopes.
And they know what they are doing.
They know what they're doing. But I think we've spoken about ourselves long enough. What we'd like to do is to answer some of your questions. Now, there have been plenty of questions sent in advance, and we'll be looking out for live questions as well, but let's deal with some questions that came in advance first of all. I'll begin with one that came from Alex Burtin. Hello, Alex. This is really for Susanne, who says, I think I've read that the time for liquid water on the surface of Mars in a thicker atmosphere and a warmer climate was around 3.8 billion years ago. Can you please run through the evidence?
The evidence, well, some of it I've already spoken about, because some of it is really that we have things like clay minerals that we now can investigate with the rover that I just showed you, but also from orbit we can see the spectral features like the light that gets reflected or absorbed by the surface, which tells us what minerals are there. And so we found the clay minerals. Clay minerals are actually something that forms in the subsurface usually, so it only tells us there is water in the subsurface. But we also have evidence on the surface, some of which we can show you in pictures, some of which you might already have seen, like you know that Mars has polar caps, which are CO2 rich and also have water ice. We also know this from orbit through spectra. But if we look at the image that you will see on your screen right now, which is a conglomerate. Conglomerate, for the non-geologists, are rocks that are made of rounded pebbles. And these pebbles are too big to be blown around by the wind. They are rounded pebbles, and if I zoom in just a little bit, what you see here is a rounded big clast on the top right. These are also NASA images that I'm showing you from the Curiosity rover mission. And this was the first finding of a conglomerate, these rounded pebbles on Mars.
But any first-year geology student seeing that would say that has to have been transported and knocked about in flowing water.
Yes.
Wind can't do it,
yes.
Flowing ice can't do it, has to have been bounced
Yes.
along in a stream.
And it has to be a long sustained stream, because if you just flush down some water through a channel, you will not get this rounding. It needs to really be rounded for a while and polished and rounded again. So that's that, but we also have delta deposits. So just the same, what you're looking at here now is just the same like river deltas on Earth. Where all of this happens when a stream goes into water and it's basically slowed down and it deposits its sediment load, the coarser things first and the finer grained things later. And so this is evidence for flowing water on Mars, and in this case by the high-rise camera, also from NASA from orbit. So we've got evidence from orbit, we've got evidence from the ground, but we've also got mineralogical evidence from the meteorites, because we find alteration minerals in them that are clearly not made on Earth, which always could be the case in a meteorite, but they are clearly Martian. And so we've got many-fold evidence for water on Mars, and we know it's mostly before 3.8, but it's also probably today, because the most recent news was these reoccurring slope lineae, which are short bursts of a fluid going down hills, for example in a crater wall, but only in the summertime and when the sun shines on that surface. So that might be even flowing water today, but that is very little. It would never make a conglomerate or something.
Yeah. Now, the viewers are interested in the Curiosity rover. There's a question coming from Edward Drecker saying, how long is it planned to be on Mars? It's not leaving, is it?
It's not leaving. It's staying. Once a rover is on Mars, it's staying on Mars.
But perhaps it means how long will it continue operating for?
Well, we are already in the extended mission. So the first mission was 2 years. But I mean, if you think, we really can't predict this. And if you think of the Opportunity rover, which was commissioned for 3 months, it landed in 2001 and it is still going. So we need to, 2004. But still, it's amazing how some of these things can actually survive. And so we knew it would survive for 2 years. We've got an extended mission now, and we just keep going.
And it's getting its power, unless I'm mistaken, from a radiothermal generator. Is that this thing at the back?
That's this thing at the back.
That's radioactive power.
Yes.
So it should keep going until
yes.
something wears out.
And that's probably what happens first. The radio power generators, they decline with time, and so we will get slower and slower because we will have to sleep more to recharge our batteries and drive a little less than we do right now. But yes, we keep going as long as it is possible. Okay.
Another question, again from Alex Burton actually, just will answer this very quickly. she's read in Brian Cox's book, Wonders of the Solar System, about the possibility of cave systems on Mars, and would those be good places for life, and are we going to send a probe into a cave?
Well, sending a probe into a cave, I can probably answer quite quickly, because once you go into a cave and you go underground, you would lose signal to Earth. So yes, we could like go in, take some pictures, come out again, but exploring a cave for days and weeks, like explorers do it here, I think we wouldn't dare to get ground control out of the picture entirely and to let this do autonomously. And possibility of life, yes, because the Martian surface has a very harsh climate, because the atmosphere is so thin, and so you've got all the irradiation. So if there were any life on Mars these days, it would possibly be hiding underground, and caves would be one option. But we don't know if there ever has been life on Mars so far, so we are still investigating that. And actually, the European missions, the ExoMars mission, is having another go at that, because Curiosity is looking at the habitability, if it's the possibility that something could live there. And so the next missions will investigate that.
Okay.
So, but I think we should go back to questions. Here's one for you, Dave. Paul Foley asks, what are the protocols for ensuring that space probes landers do not contaminate a moon that may have life on it?
Well, Paul, you can't ensure anything. All you can do is minimise the risk. Now, there are internationally agreed protocols set up by a body called COSPAR. That's I forget what it stands for, something to do with Committee for Peaceful Uses of Outer Space or something.
Yep.
But there are these protocols. You have to make sure that any spacecraft that's going to land or accidentally crash onto a body that's potentially habitable, you have to make sure that's as clean as possible and as sterile as possible. Yep. But you can't eliminate all the microbes on the surface. There will be a few hundred per square centimetre or something.
Yeah.
Most of those will die in the flight from Earth to Mars or Earth to Europa or wherever, but a few will survive, and a few that survive, if you land somewhere habitable, they might be able to hang on and start to metabolise. So you can never eliminate the risk, but you have to make, I checked the rules. We've got a website where we can show you that you can go and find the information for yourself. But Google planetary protection protocols and you'll find the answer. The rules are that in a 50-year period of exploration, there should be less than a 1 in 1,000 chance that you're going to contaminate something. Go here, this is a NASA site which will tell you, it links to the COSPAR protocols. All you can do is minimise risk, and the standards of cleanliness that are required vary with your target body.
Yes, and there are rules as well, like we with our RTG that we spoke about, we would bring a certain heat source, because whatever generates energy, electrical energy, also generates heat. And so we would not be allowed to go anywhere near where we think there is liquid water or ice up to 1 meter below the surface. That's different for other probes, like the Phoenix lander, which landed on the Martian pole. That one had solar panels, and so the moment when the winter sets in and the snow covers the solar panels, everything gets really, really cold. And as far as we know, everything would die then. And so that's the difference in the different rules that we have to actually make sure that we don't bring anything and then don't know whether we just brought a life to Earth and find this again, or whether we found really genuine Martian life.
Okay, I'm looking for a live question now, and there are quite a few live questions. One from Rod. Do we know of any meteorites with an origin outside the solar system? Don't think we do. There are components of meteorites from beyond the solar system. There are some pre-solar grains.
Yes, they are older than this.
And calcium aluminium inclusions. But
calcium aluminium inclusions, silicon carbide, diamonds as well, that they have found on the nanosims by the isotopes that they can measure. But these are tiny, tiny grains. When I say nanosims, that's a few micrometer. If I had this here, there wouldn't be a camera around us to zoom in enough so we could show them to you, because I couldn't even see them with the naked eye. You would need an electron microscope or something.
Tiny little grains, no whole meteorites. And VIR is saying, if the moon were further away from the Earth than it is, how would tides be affected? Well, if you've seen our Myth-Busting Moons video, you'd know that almost half the tidal range on the Earth is due to the sun affecting the oceans. So if we lost the moon completely, we'd still have tides. But if the moon was further away, the lunar tides would be weaker. And the difference between spring tides when the moon and sun are lined up and neap tide when they're at right angles would be reduced. But we'd still have tides because of the sun.
Yeah.
Yeah.
Shall we stay on the moon a little bit? Because we have a question from John Joyce. It says, in your opinion, how likely and when do you think our species will establish a base on either the moon or Mars?
Well, I remember the Apollo landings, and then it was, in 20 years' time we'll have a base on the moon, and it hasn't happened yet. It's always receding 20 years into the future. Clearly, technologically we could do it. I think the Chinese might well be heading up to do that. They could be on the moon with some kind of semi-permanent presence in the next 10 years. They've landed with very successful rovers. They have heavy lift capacity.
And there are lots of designs as well, how we might want to build a habitat there.
Yeah, well, the European Space Agency, I think it's on screen now, has plans for lunar bases, or they've done feasibility studies. Here's a lunar base. They're using 3D printers to make some of the components out of a lunar regolith and so on. It could happen if we put our minds to it. Whether that will happen before Mars, I don't know. I mean, Buzz Aldrin is going around saying, get your ass to Mars. He thinks Mars is the most important destination. Leave the moon aside for now. And maybe NASA will go for Mars next.
Yes, I think we have one problem when we want to go for Mars, and that's the long duration space flight, because it takes actually 7 months to get there, and then you have to be on Mars for over a year, so the orbits align up again, so that you then can come back, and so you are in a spacecraft again for 7 months. And we just had on the International Space Station, for you who might follow that one, on the International Space Station we just had 2 astronauts, Michael from Russia and Scott from America, who stayed there for an entire year. And Scott Kelly, the American, was especially an interesting study subject, because he's got a twin brother who stayed on Earth, and so they can actually look at the changes in a human body when they are out there for that long, because there's cosmic irradiation, there's the weightlessness, there are lots of things that we are not used to. And then the difference between the moon and Mars is, if something happens on the moon, you are back in a day, or in 3 days at maximum. You have a 7-month difference in space flight time to Mars, and so if anything goes wrong, sending extra supplies or bringing someone back is a much different story.
Quite apart from the long duration, what about the planetary protection protocols? It seems to me, as soon as you take a human being to Mars who's going to breathe out and go through an airlock and bodily waste and so on, as soon as you do that, you've not got a 1 in 1,000 chance of contaminating it. You're certain to take some viable microbes to the planet.
Yes, and so a lot of scientists are actually arguing we should make sure that we have established whether there is life on Mars or not before we actually take humans there, and before we actually think of building a base or something. And I think from a scientific point of view, there's certainly something in that. Find out first and then go there.
Okay.
So here's another one from the moon, actually. Derek Binns asked, the rills of the moon, how did they form? Do they suggest liquid in the moon's past? And if so, which liquid?
Well, yes, they do suggest liquid. For those who don't know what a rill on the moon looks like, here's a view on screen now. Snaking from top to bottom across the middle part of our image is Hadley Rill. It's a sinuous rill. It's a couple of kilometres wide. It was produced by a flowing liquid, but it's not water, it's lava. Now, we don't know whether the lava is thermally eroding its substrate, which is also a lava plain, or whether it's a collapsed lava tube. But we're pretty confident these indicate flowing lava. In fact, we've been there. This is where Apollo 15 landed. There's another image showing an astronaut on the surface. Here's a view of from one of the bends of Hadley Rill with an astronaut and the rill beyond him. But that was an amazing picture. It's one of my favourite pictures from the lunar surface. That was the first mission with the lunar rover. So the rills, at least for sinuous rills, we understand they're carved by flowing lava. Now, we wanted to look at more live questions. There's a lot coming in. Are there plans to send a similar rover? I guess that's to Mars Curiosity, similar rovers to another planet or to a moon. The Chinese have a rover at the moment on the moon.
There's the little U2.
I think it's not moving anymore, but it's still alive.
Yeah, it's still, I think, sending pictures back. That's the last I had heard.
And the Chinese will try sample return from the moon. There's a European rover that's going with ExoMars to Mars.
Yes,
yeah?
there's Mars. I mean, for Mars, there are lots of plans. For Mars, there is, first of all, the 2016 lander. So that's not a rover, that's just a landing attempt from ESA, or landing from ESA, soft landing. Of an object that has a very few science instruments because it's a technological demonstrator. But in 2018, the ExoMars rover will go, and that's a very versatile rover. It's totally different from Curiosity, because what it actually shall achieve is it wants to drill 2 meters deep, because the Martian surface is fairly harsh, and organics from past life might not have survived in their original state. And so that's why ESA really wants to drill deep to find out whether they find organics that would speak for life, the question that we had just a moment ago. And NASA is going to go in 2020 with a Mars 2020 mission, which is actually the same base like the Curiosity rover, but it's got a different payload, as we say. It's got, for example, inside MOXIE, which is an instrument that makes oxygen out of the Martian atmosphere. And if you hear that, you would think, why would you want to do this? Well, actually, because NASA is planning to go back and to look at, to send to send astronauts and not just rovers. And so they are step by step, like they did this with the Apollo missions, are building up their engineering capability to actually step by step learn what they need to do.
So a relevant question from Torman here. Why all the effort to explore Mars when we haven't even scratched the surface of our own moon?
Well, that's probably one for the two of us, because you're more in the moons and I'm more in the planet. I think they are both equally valid. And our moon is currently a little bit less in fashion, shall I say, because people really want to answer that one big question: are we alone in our solar system? And you can't answer this on the moon. There is no water. There is nothing that would indicate that it ever was habitable. Or do you think different?
Well, there is a little bit of water in minerals, and there's water in permanently shadowed craters near the poles, but we're not thinking of environments that look as if they were habitable, such as Mars had in its deep past, and such as occurs today, we think, in the internal oceans of some of the icy moons like Europa and Enceladus. So a big driver for exploration is to prove that there are places which are habitable, and if we can, to demonstrate whether or not there is life there, because it's such an enormous question. If we find life anywhere in the solar system that is not related to life on Earth, but had an independent genesis, and if life has started twice in this one solar system, then with all the other habitable places there must be in our galaxy, because we know there are lots and lots and lots of planets with stars. More stars have planets than don't have planets. There are lots of exoplanets. They must have habitable environments. So if there's a habitable environment, does life get started there? That's what we don't know. If we find it twice in one solar system, then we'll be pretty certain that there ought to be life everywhere. I mean, it's such an enormous question.
It is. And it's probably the one that's always has sparked most fantasy and most curiosity. Are we alone? I mean, that's the most fundamental question I can actually think of.
Yeah. And we didn't mention that planetary protection is meant to work both ways. It's not just stopping us contaminating or taking terrestrial microbes to Mars or Europa. It's preventing the accidental bringing back. If you've got a sample return mission, you've got to keep the sample isolated and not let Martian bugs loose on the Earth. But I think fears that you're going to bring back Mars plague to the Earth, I think, are pretty ridiculous, because anything on Mars is so weakly related to life on Earth. It's not going to be infectious in any way.
Yes, one would hope so. But, you know, I think space agencies have always played this safe. When they went to the moon and they didn't really know, they put the astronauts into quarantine before they let them out. And that was the way to prove it. And so, yes, we need to play it safe in a way. And that's what planetary protection both ways is for. And we actually have a question that relates to Europa. Kate Reed says, I'm very excited about NASA's upcoming mission to Europa. What temperature is the internal ocean thought to be, and would any sunlight be able to penetrate through the ice?
Okay, well, NASA has a mission to Europa which used to be called the Europa Clipper. It may not have that name now. And there's a European Space Agency mission which is on screen now, or will be shortly, I think. NASA's ESA mission to Europa is called JUICE, which stands for Jupiter Icy Satellites Explorer. They've taken the right letters to make a pronounceable name like JUICE. So here's JUICE on screen. That's going to orbit Jupiter and have several flybys of Europa and of Ganymede. Now, Kate's asking specifically about Europa because, as I think she realises, that's the most likely one to host life. The surface of all the satellites of Jupiter is very cold, something like minus 100 centigrade, I forget the exact value, but below a few kilometres of ice, we think there's a liquid ocean internal. There's about 100 kilometre layer made of water. The outer part is solid, the inner part is liquid. We don't know the balance between them. But once you're below the ice, you've got liquid water. That must be at least 0 centigrade, or a little bit below if there's some salt. But that's warm enough for life. So it's going to be above freezing, but the sunlight is actually not an important consideration for life, surprisingly enough, because you do not need sunlight for life. There's plenty of life on Earth. In fact, the places where life on Earth may have begun is deep in the ocean, where you've got warm water that's been heated by contact with warm rock coming out through hot springs on the ocean floor. They're called hydrothermal vents. And the water that's flushed through the warm rock has picked up chemicals, and those chemicals provide chemical energy for life. It's called chemosynthesis rather than photosynthesis. So there are chemosynthetic bacteria on hydrothermal vents at the Earth's ocean floor that turn hydrogen into methane, for example, and you can get energy out of that. So that's the basis of a food chain, and at the vents on the Earth's ocean floor, you have sort of microbes like bacteria doing this. Then you have crabs and shrimps grazing on this stuff. And if the sun were to disappear, these little ecosystems would carry on. And maybe there are ecosystems inside Europa that don't need the sun.
Yeah, there's a surprising variety of things living down there if you look at the pictures that they get from these deep diving vessels. On
the Earth's oceans, yes, but the higher organisms on the Earth have evolved in the photic zone and migrated back down. If all you ever get is things living off chemical energy, maybe it doesn't get a chance to evolve to anything higher. We don't know. We'd like to find out. But there are ways to get sunlight on Europa, because the surface does crack apart. But maybe there are places where the cracks open and close tidally, once per orbit. That's every 8 days or something in the case of Europa. So when a tidal crack opens, water is drawn up into the crack. When the ice sheets close again, some frozen slush is squeezed out, which is a way of sampling the ocean, just go to the frozen slush. But while the crack is open and water's drawn up, there's a chance for things to photosynthesize. In the top bit of the ocean, the top few meters, I mean, Jupiter is 5 times further from the sun than the Earth, so that's 25 times less sunlight, but that's still enough for photosynthesis. It's like a cloudy day on Earth. So you could have photosynthetic organisms in the cracks, but a much greater volume accessible to life at the floor of the ocean, tens of kilometers down, living off the chemical energy. So yeah, we've got a chance of a food chain, and the missions to Europa are not, the initial ones are not going to land, still less drill through the ice, but if you look and try and analyse the ice that's squeezed out through the cracks, or look for ice vented to space, if there are plumes coming off Europa, which is very controversial at the moment, but there's certainly plumes vented to space from Enceladus, the moon of Saturn, where the ocean is being sampled, and that's being gushed out to space. Take the right instrument and fly it through a plume, you might find molecules created by life. So there are ways to sample without landing and drilling.
That would be very interesting.
They are decades off, sadly.
Yes. But, well, we might get there at some point. So, and here's another one, actually. Paul Horth asks, why is that we do not see moons with their own moons? Is such a system inherently unstable?
Yes, well, Paul's quite right. There are no moons of moons known. And I guess it is that they are unstable. If you look at the innermost planets of the Sun, Mercury and Venus, they don't have any moons. It's because the volume of space controlled by the planet is small compared to the volume influenced by the Sun. And when we go out to talk about moons going around planets, the moon would be sort of in gravitational control, if you like, of only a small volume of space. The rest will be disturbed by its planet and by the Sun. So you can't have a moon orbiting the moon in a stable situation. When we put an artificial satellite in orbit about the moon, its orbit will decay over months or years unless we do things to keep it in place. You could have a more stable orbit if you tried really hard. But a natural satellite of the moon wouldn't stay in place for millions, let alone billions of years, because it would be inherently unstable. So I think you're along the right lines there, Paul. Let's look for some live questions. Well, Shura is asking about the analyses of the Enceladus flyby in 2015 by Cassini and what are the results. I haven't heard them yet. Cassini is the NASA and ESA mission that's been orbiting Saturn for over a decade now. And it had its last close flyby of Enceladus late last year. And it was flying through the plume at the lowest possible altitude, and there were hopes it would be able to detect molecular hydrogen.
So maybe they're still analysing the data?
Which will be a product of living processes, and the data have not been released yet. So, sure, I can't answer that. The whole world's waiting to find out. It's been longer than I expected.
Well, maybe they need to...
We're both off to the Lunar and Planetary Science Conference in a couple of weeks, aren't we?
Yes, we are.
We might find out there.
That's true, yeah. But it's probably they need to calibrate their instrument and make sure that they actually know what they are seeing there. Because one big thing is if you run an instrument, yes, you of course calibrate this on Earth before you set it to space and fly it where it needs to be. But on that flight, a lot can happen. So you need to make sure you measure repeatedly standards, like things that you really know what they are when you bring them, that you bring with you, so that you really can test the performance of your instrument. And that's been done repeatedly. And then if this is done repeatedly, they might have to just cross-check things. We are doing this regularly on the Curiosity rover, and every single spacecraft does this very regularly to just make sure the numbers you get are still the numbers you expect or nothing has happened. One big thing is that solar irradiation actually hits the CCDs that are in cameras, and you need to correct for that. So you sometimes have just white pixels, which are white pixels because a ray has hit there and has destroyed that pixel.
Question from Dave Arnott, which I've just lost from my screen. Here we go. Do you think extracting metals or other valuables from the Moon, Mars or an asteroid is ever going to be a realistically viable enterprise?
Not probably for Earth.
Not to bring back to Earth, but...
Well, the moment you are there, you want to resource everything from where you are, because the highest cost is always the transportation cost if you think transporting something from here to the moon or back. And that's why in the picture you showed earlier, they are trying to 3D print from the lunar regolith. So they are trying to use the materials that are there. So the moment we are establishing any long-term duration on any celestial body, be it the moon, be it Mars or anywhere else, then we need to understand and mine these resources.
The two commodities I've heard of which might be economic to bring back to Earth, one is helium-3,
yes,
which is supposedly embedded in the lunar regolith. You have to process a lot of lunar regolith to get helium-3, to get enough helium-3 to be worth bringing back to Earth. When you get helium-3 back to Earth, supposedly you can use it as fuel in nuclear fusion reactors, but we don't yet have the technology to make a nuclear fusion reactor. So in the future, if you strip mine the lunar regolith to extract the helium-3, it's a long shot. The other thing is platinum group metals from iron-rich asteroids may be worth bringing back.
There were talks about catching an asteroid and bringing it in closer to Earth, things like this. They are discussed, and some are more serious than others, but certainly we need to be able to do these things the moment we want to live there for more than a couple of days.
Yeah, and Nigel's saying, what about solar power from the moon via solar panels? If that's solar power to send back to Earth, you don't need to go to the moon to collect that. Just put solar power panels in orbit around the Earth if you've got a way of beaming the power back down to the ground. That's the difficult thing, getting the power to the ground. But you don't need to go to the moon to get sunlight. Once you're above the atmosphere, you can do that.
Yeah.
Okay.
I would think so.
Now, here's one, I think, for you, Susanne. Alison Bramley is saying, Can you tell us a bit more about Martian meteorites, please?
Oh, with pleasure. I actually got my PhD studying Martian meteorites, the noble gases in them. Martian meteorites come in 4 groups. There are the shergottites, which are basalts as we know them. Then there is the Allen Hills 84001, which got infamous at some point because someone claimed they had found something that looks like life, but that's later got disproven. And there is Chassigny, which is thought to be a piece of the Martian interior. And now we've got a regular breccia as well. But actually, I've got a piece here. And if you want to hold a Martian meteorite for a second.
I never get tired of this.
I can believe that you never get tired of this.
I'm holding a piece of Mars. I mean, it's what's called a thin section, where you cut a thin slice of rock, then polish it away until it's thin enough for the light to get through. 30 microns is the conventional
Shall
thinness.
we have
Let's take a
closer look? Because Dave just spoke about how thin this is. All you can see here actually is a glass slide, because we put these rocks onto a glass slide, because everything else they would just crumble and break. The rock that's on there now has the thickness of a human hair, about 30 micron. And if I put this down this way now, what you see here is this thin section, and that you can actually look through this thin section. And what you see on top of here is a little bit of a dark rim. This is the melt rim, the fusion crust, and that happens when the meteorite comes into the Earth's atmosphere and it's heated in a flash, and the rock on the very outside melts. It's just a few millimeters that at maximum survive, or even less so than what as you can see here. And then you can see that this meteorite also has 2 areas, and that's the one area which looks a bit more fine-grained, and that little appendix here is the area where it looks a bit more coarse-grained. But of course, in the resolution you are seeing that here, you can't really see much of it. But there is actually a way around this. I can show you the virtual microscope, where you will see that we can take this rock, we can put it under a microscope, and we can look through it and do a lot of things with it and scientific investigations with it. What you see here is the landing page of our virtual microscope at www.virtualmicroscope.org. And if I now go into the page that I have opened previous to that, you see the exact same picture, just in much better resolution. And what I can do here is I can even zoom in, and I can show this in much bigger detail. And what you see here is that you have things that look brownish, and that you have things here that look almost transparent. And I can now switch the light source. What you have right now is, let's call it regular light. It's actually plain polarized light. And I can make this light special and make it crossed polars, so that only certain wavelengths get through here, and the minerals that before were brown are now in all sorts of multicolors, and these are the pyroxenes. And then there's this, what was white before is now black. And that
they're all black, aren't they? Those clear minerals have gone,
yes.
Every last one is black, so
yes.
There's no, in cross pole there's no lights getting through.
So that's a glass.
Yeah.
And glasses generally are formed by impact shock. So how did this rock get here? Well, they are getting here because another rock, a very big rock, hits Mars and ejects these rocks to come to Earth. And now that they are actually coming to Earth, we can study them. And if we can quickly switch back to the screen for a moment, then we see what I told you earlier. You see now on the right-hand side of your screen this coarser-grained end piece, and on the left-hand side of your screen the finer-grained things. And so there are 2 lithologies, 2 different types of rock in this one meteorite.
Can we get the left-hand end and rotate it? I can see that rotation centre.
Yes.
People will like to see that. It should be
So
pretty.
what a petrologist does is they look down a microscope and they start, and on the left-hand side you now have the normal view, on the right-hand side you have the crossed polars, where we just discussed that all the glasses are black. And now what I can do is I can take my cursor and I can rotate this on the screen, and you can try this at home actually. And you see that especially on the right-hand side, minerals change their colors. And what you can do, if I look at this very big one that's now at an angle on the very right side of the screen, I can turn this and you see that it gets almost totally black, and then if I turn more, it's the brightest color it can get. And where it's get entirely black, that's called the extinction angle, and you can even do chemistry with that.
Okay. Elaine Duarte is wanting to know when this meteorite landed. Do we know when it landed?
Not for specifically this one, but there is a wide range. Some landed about 1 million years ago, and they are usually from Antarctica because they survive nowhere else.
Yeah.
But on the other end, there are observed falls. The Martian interior meteorite, Chassigny, fell in France in 1812, and it was observed and it was collected.
Okay, so this is from Antarctica, collected.
This is the one that I showed is collected from Antarctica, and it is an RBT meteorite collected in 2004.
And how do we know it's from Mars?
That's a very good question. Well, we go and investigate the chemistry in a lot of detail, namely with isotopes. And so oxygen isotopes are different on Mars than they are on Earth. And so if we measure the oxygen isotopes, we know that they are from Mars by that measurement. But before we even had discovered that, there was something else. There was the Viking mission in 1976, which measured the Martian atmosphere. Curiosity has now measured it again, by the way. And that measurement had the noble gases in them, and the noble gas xenon had a very special 129 to 132 xenon isotope ratio. And in that glass that we just had been talking about, in the meteorite Allen Hill 77005, that same composition was found. And because of that, they could make the link between Mars and these meteorites.
So we've definitely got bits of impact ejector from Mars which have made it to Earth.
Yes.
Now, see, I think that means if there is life on Mars, over the past billion years of Earth history, we must have had viable microbes from Mars hitching rides in these meteorites.
Yes.
So if there's life on Mars, it's already infected the Earth. So we're immune to Mars plague, folks. Don't worry. We'll survive whatever we bring back in a spaceship.
Maybe we are all Martians because Mars has a smaller diameter, so with its surface would have been colder earlier than the Earth's surface, potentially.
Well, yeah, this is a very good point, because we don't know. If we do find life on Mars, we won't at first know whether it began on Mars and came to the Earth, or began on Earth and spread to Mars, or began separately in the two places. That's the big thing to find, life beginning independently in two places. But Earth and Mars have been swapping materials throughout the lifetime of the solar system, so life on one could have spread to the other.
Yes,
Whether it could get as far as Europa, I don't know. That's a much bigger ask to get from Mars to Europa.
And it's also a bigger ask to get from inside to the outside than to get from the outside to the inside. That's why we probably have more Martian meteorites on Earth than Mars has Earth meteorites on its surface.
Yes, John Joyce, we are talking about panspermia from Mars.
Yes.
Yeah.
And so these microbes could hide in a rock, so to say, like, because space is a very harsh environment. It's desiccating, it's vacuum, it's very cold. You don't get around the cold, but if they are enclosed in a rock or maybe in a mineral enclosure, they could actually survive quite a bit of that. And there have been experiments that they survive the impact shock and all of this.
Yeah. I think we've used up our time, really.
It always goes very quickly,
It goes very quickly. Look, thank you so much, everybody, for answering the questions. There were more questions than we could deal with in advance and live. That's great to know. Please, before you disappear, tell us what you're studying. I can see a lot of people have had a go at that widget. And just over half are doing the Moon's MOOC, and a quarter are currently doing S283.
Okay.
So that's nice to know.
Do they want to go to Mars?
We haven't got a voting option for that. Oh, but where should we send people? It's fairly evenly balanced. Well, 29 want to go to the Moon next, and 17 want to go to Mars next.
Okay.
The balance has tipped a long way, but I think it's either down that way or that way, or dead level. So, one more vote for the Moon. I mean, I think it's probably going to happen with the Moon. There are more the organisations aiming for the Moon. Only one realistically could get to Mars in
Yes,
the next,
yes.
in reasonable planning time, which is NASA, and they haven't quite made their mind up to send people.
Well, but they have MOXIE in the Mars 2020, which is a first step.
Yeah. So, thank you, Susanne, for giving up part of your evening and for bringing along and letting me hold a piece of Mars.
Thank you for having me here.
Really enjoy that. We'll try and do this again in the autumn. I mean, whether you're studying S283 or the moons will have moved on by then, but you can keep in touch via Facebook and Twitter and other means. So we'll probably put something on in the autumn for the people starting the Level 2 Planetary Science course S283. So until then, thanks for listening, and thanks to the guys and girls in the back room for making this possible, and good night.
Good night.